Hello everybody. In this video we're going to be covering section 16.1, Spontaneity. For our learning objectives, we're going to first distinguish between spontaneous and non-spontaneous processes, and then we're going to learn how to describe the dispersal of matter and energy that accompanies certain spontaneous processes. So first off, what is spontaneity? Basically, we've observed in our everyday lives that processes have a natural tendency to occur in one direction when we have a certain given set of conditions. All right, so water will naturally flow downhill, but it doesn't just naturally flow uphill, right? We have to input some energy to make that happen, like by adding a pump. If we extend that to like chemical processes that we see, iron, when we expose it to air, is going to corrode and produce rust. All right. But rust is never spontaneously converted back into iron. That requires smelting, which is a chemical process where we input a lot of heat and certain reactants to make it happen. So we need a lot of a lot of energy to get the reverse to happen. A spontaneous process is one that occurs naturally under certain conditions. So water spontaneously flows downhill, iron spontaneously corrodes into rust. A non-spontaneous process will not take place without the continual input of energy from an external source. So we've talked a bit about reversible processes, right? These are processes that can go one direction and then go back the other direction. So let's talk about how that relates to spontaneity. So if a process is spontaneous in one direction under a particular set of conditions, it's going to be non-spontaneous in the reverse direction. So if one direction is a spontaneous reaction, the reverse direction is not going to be spontaneous. We're going to have to input energy to get it to go back the other way. At room temperature and typical atmospheric pressure, for instance, ice will spontaneously melt, but you never observe water spontaneously freezing at room temperature. An important thing to keep in mind here is that spontaneity has really nothing to do with the rate of a process, okay? A spontaneous change may be rapid that it seems instantaneous, or it could be so slow that it's basically almost never observed to happen. And a good example of this wide variety is the decay of these two isotopes here. So if you have uranium-238, uranium-238 has a half-life, and we learned about what that was in the kinetics section. That's like billions of years. So for all intents and purposes, it appears to never really decay over any kind of reasonable time frame that we're measuring. Whereas technetium-99, this stuff is used in medical applications and stuff for like imaging, and the reason is because it decays very, very rapidly, okay? Because you don't want radioactive stuff just kind of hanging out in your body. So even over the course of a couple of days, it will go through many, many half-lives until it's essentially gone. And both of these reactions are spontaneous. One is just much, much faster than the other. Another example would be like diamonds, okay? So this is more of a physical process. We're not having a chemical reaction here exactly, but the most stable form of carbon, this most stable allotrope under high pressures and temperatures would be the diamond. And the most stable form under the ambient, like atmospheric pressures, is going to be graphite. So that means that diamonds, when they're in our everyday world, they are slowly turning into graphite. But that process happens so slowly that they're essentially stable. But they are spontaneously turning into graphite. So let's talk a bit about the dispersal of matter and energy, and this is really going to lead into our next topic that we're going to be talking about, which is called entropy. But it's first important to kind of get the conception of what entropy is before we get into the math of how it works. So let's start by considering an isolated system consisting of two flasks, okay? They're connected with a closed valve, and initially there is gas on one side and the other side there is vacuum. We know that when we open this valve right here, The gas on this side is going to flow into the vacuum side until they're even and the pressure is the same on either side, right? We have relatively the same amount of atoms on either side at that point. But why does that happen, right? Most of our arguments about this would have been that the internal energy of this system has gone down. It was able to release energy, find a lower energy state and stuff. But if we consider the system that we have here, we haven't done any work, okay? Because work would have implied that we were pushing against some pressure on the other side here, right? This gas going over here isn't doing any work because it's not pushing against any other atoms or any other pressure on that side. So work is 0. And since the system is isolated, meaning that we're not allowing heat to transfer in and out, then the heat transfer has been 0. Okay, so Q is 0. And if we go back to our definition of internal energy and we take a look at that, that's Q plus W, which means 0 plus 0. So there's been no change in the system's internal energy. There's no reason that that argument would fit for why that happened. Instead, what's happening is that the spontaneity of this process is being driven by another force. And basically, that force is that systems are going to tend to want to go towards greater and more uniform dispersal of matter. All right. And that's exactly what we did, right? We had localized matter here, and then when the process happened, we had it more evenly dispersed. All right. The matter was distributed more widely, meaning that it occupied twice its original volume, and it was more uniform. Okay, so it was present in equal amounts on either side of the flask. This could also be extended to energy. Energy also tends to want to do this. So if we consider two objects at different temperatures, I have a hot one and I have a cold one, and then I bring them into contact, heat is spontaneously going to flow from the hot one over to the cold one, right? The hot object loses energy and the other one gains it, but there was no net gain or loss of any thermal energy, right? No work is being done here either, right? Because nothing's expanding or contracting. And because no heat left the system, that is the two blocks in this case, Q is 0. The only thing that's driving this to happen is that there was a greater redistribution of heat between the two objects. All right, and that is a thing that we're going to see over and over again, is what winds up wanting to happen in most spontaneous processes.